Okay, so today I'm going to try to talk about fuel metabolism during exercise. So, what is the total energy expenditure and its main component, and also which factors does it depend on, and what is indirect calorimetry and respiratory quotient? So, first of all, what is the total energy expenditure in other words? So, it's basically the sum of all the calories that your body would burn during a day and is composed of basal metabolic rate, resting metabolic rate, physical activity, and thermogenesis. So, the basal metabolic rate is basically the minimum amount of the calories that the body would need to perform digesting food, breathing, pumping up blood, keeping a stable body temperature, and also maintaining some chemicals in our body. And the resting is the amount of the energy that the body would need to function while at rest, so eating, walking for very short distances, sweating, or shivering. And is like 70% of the whole total energy expenditure. And the physical activity also composed of like a percentage of the total energy expenditure, but it depends on the duration and how intense we train, and also which type of muscle tissue we use, if it's type 1 slow twitch or type 2 fast twitch type of muscles. Also thermogenesis, so basically when we eat, consume food, how much calories we use to catabolize it, so basically to build up amino acid or store glucose as glycogen. What is the total energy expenditure and its component? We already gone through that, so now I'm going to try to explain what is the indirect calorimetry method. So it's actually a way or a method of measuring resting metabolic rate. So the idea behind it is that the body releases energy when we burn oxygen or when we use oxygen, and at the same time produce carbon dioxide. So if we measure how much oxygen we breathe in and carbon dioxide we breathe out, we could calculate how much energy we are using from different macromolecules. So basically, which energy we are using in this process for lipid, carbs, protein. And usually this measurement is done after fasting 12 hours and is full rested in a quiet area 30 minutes. And this method is being right now concluded in a table, which is right here. So basically, what does this tell us? This tells us that the RER is basically the I think respiratory expenditure. So basically, it tells us, like, depending on how much calorie of oxygen we are consuming or using, which type of macromolecule we are depending on. So basically, when RER are 0.71, we are not using so much oxygen, so we depend on fats as an energy source. But when we see that here, when energy is increased, the calorie of O2, when it measured at its highest, we are now not consuming or not depending on fats for energy sources, but rather on carbohydrates. And also the RER got increased. So basically, what does this tell us? This tells us that which fuel our body would use during exercise. So when we breathe more oxygen, we use more carbohydrates. But in low intensity exercises, the body would not depend on carbohydrates as a source of energy, rather more the fat one. Okay, and body stores of fuels and which tissue or organ provided during resting metabolic rate. So basically, this is just to explain which tissue store which type of source. So basically, you have carb, which is stored as muscle glycogen and liver glycogen, also as free glucose in the body fluid. And fat, we found it in the subcutaneous and visceral tissue and also intramuscularly. And which tissue or organ would need the most energy during resting metabolic rate? So when we wanted to perform the normal function of them. So the liver and kidney and brain and the heart actually needed 60% actually 60% of the total energy expenditure to keep doing its function. And actually these ones are, I think, 15 or 40 more times needed of equivalent energy more than the muscle uses, say. So the muscle doesn't need as much energy from the total energy expenditure. And what are the factors that could affect the resting membrane, or not resting membrane, but resting metabolic rate? And it is the tissue which needs the energy the most and also are dependent on tag cycle. So the liver, kidney, brain, the heart actually needs more energy, and that is one of the factors that could affect the resting metabolic rate. So which energy it should give out to which tissues. But also the triacylglyceride cycle, because the triacylglyceride cycle is important. Why? Because you have free fatty acid that could be broken down from the adipose tissue during lipolysis, or during like when we have glucagon that is dominating the blood, and this free fatty acid could then be transported in the blood and is transported for fuel for tissues, and then being incorporated with glycerol 3-phosphate and producing tag molecules for the liver. But also the liver could then break down the tag to free glycerol and free fatty acid and then store it in the adipose tissue again as tag. So that's why the tag cycle is important. And also other factor because why the tag cycle is important, because these tissue, the liver, kidney, brain and the heart, would need triacylglyceride as a source of energy sources for them, and not glucose or protein, so they depend more on the fat side. Also, you have other factors as age, gender, genetics, pregnancy, hormones, and you could read the rest of the factors that could affect the resting metabolic rate. Okay, so with the three energy system and the relations, so we should explain right now which three sources of energy we have during exercise. And these three sources are basically the ATP phosphocreatine system, and is actually dominating in the first 5 to 10 seconds, and is basically using the ATP stores in our body is decreasing at this point. Also, it uses phosphocreatine to generate energy during this system, and I will be explaining soon how it does that. Also, anaerobic glycolysis is active during high moderative intensity and is ranging from 10 seconds to 1 minute, and this uses ATP from the muscle and glycogen, and it's stopped because of hydrogen ions production, which leads to fatigue, and also because of the pH drop due to accumulation of lactic acid. And also how much glycogen we have is also affecting the anaerobic glycolysis, because if we don't have high levels of glycogen, so if we've not eaten enough glucose levels before the training and stored them as glycogen, then we can't really use glycogen during fasting, like not fasting, but during high intensive exercises. So this is also one of the issues with anaerobic glycolysis. And aerobic glycolysis would happen during very low intensity training and range usually from 2 minutes up to 2 hours, and produces most of the ATP, but takes also the most time to use it. So this is also another issue with glycolysis. So not the issues, but this whole system depends on like nutrition. So the ATP phosphocreatine system depends on creatine to then be converted to phosphocreatine by creatine kinase, and then from there store the phosphocreatine and then use it during training. Also, anaerobic glycolysis depends on the amount of glycogen we have in our body, so the colloq cycle is also limitation of this source of energy during our training. Also, aerobic glycolysis is also actually depending on the glucose as a source to do glycolysis. but also it takes so much time to use it. We can't really use aerobic glycolysis during intensive training. And this is a problem because sprinters who are like training for like who have maybe is putting effort in the sport and try to achieve something usually do have issues with the anaerobic glycolysis because the phosphocreatine system. Also another problem with phosphocreatine system, not only the nutrition part, but it ends so fast. Like it provides you with energy the first 10 seconds. After the first 10 seconds, you're done. You're basically right now switching to anaerobic glycolysis. And if you're not trained enough, or if you don't have as like much levels of glycogen, then you would produce lactic acid and hydrogen ions, and this would lead to muscle fatigue. So when you're muscle fatigued, then you can't really contract and you can't do your exercises or sprint as good as you would if your muscle wouldn't be fatigued. So this is also another issue with this system. Okay, and let's see the next thing we have here. Yeah, so this is the phosphocreatine system. So as you see, guys, this creatine right here will be converted to phosphocreatine, and this is during like fed state. So when we eat dairy products, because we need to consume glycine, arginine, and methionine to produce this phosphocreatine. When we have high levels of creatine, we could store more phosphocreatine and use them during contractions. And this is why some people cheat during, or not cheat, but they try to cheat their way in tournaments by using creatine as a supplement, because when you eat more creatine you get more phosphocreatine, and you could use more phosphocreatine here, because what the phosphocreatine does actually here. So we are resting, we have phosphocreatine and ADP, but when we contract, this phosphocreatine will give, so it will be ADP plus PE producing ATP right here. And when we have ATP, we could contract. We could go all the way here, and it leads to contraction of the muscle. And this is why phosphocreatine system is important, because it donates its phosphate group and add it to the adenosine diphosphates and create adenosine triphosphate. And this is why this is so good, because we are regenerating these levels of ATP once again, because this is actually a reversible step, but it's not shown here in the pathway. And this is also why this phosphocreatine system is so good, because it provides energy. And this is also like the reasoning why people take creatine as a supplement, because they want to store more phosphocreatine, and in case of contraction, phosphocreatine is giving away its phosphate group here to the ADP and creating ATP once again. Very simple understanding of this system, but it depends on how much creatine you have been intaking, and this is also dependent on the food intake, of course, but also it doesn't provide you energy for more than 10 seconds, so this is also another issue. Okay, and let's see the next thing. Yeah, aerobic energy system. Yeah, so we have this gas exchange of oxygen and carbon dioxide, which will then go to oxidative phosphorylation and citric acid cycle, and from there produce ATP during ETC, of course. Also you have here, so if you have glucose from intestine or in the liver, free glucose is going out here, and then you have glycogen also is breaking down to glycolysis or to glucose, and then glucose is used to create pyruvate, and from pyruvate acetyl coenzyme A, and then going to the citric acid cycle, or this pyruvate could then produce lactic acid. And this process right here, not right here, but this process right here is called the Cori cycle. So this Cori cycle is also very important right here. And what is oxidative capacity? So the oxidative capacity is the ability to gain ATP through aerobic metabolism. So what do I mean by this one? So I will be explaining this right now. And it's a measure of the muscle maximal use of oxygen. And the first factor that actually is depending here is enzyme activity. So, of course, these enzymes that dominate in the mitochondria is important. So as succinate dehydrogenase, malate dehydrogenase, carnitine palmitoyltransferase, these are aerobic enzymes, and for aerobically trained people, these are increasing. So it will help you use more oxygen efficiently. You understand? And also the second factor that affect this oxidative capacity is the type of tissue or type of muscle tissue which are dominating. So the red is the slow twitch, is more aerobically active, and it's because it have more mitochondria, more myoglobin, and is high resistant to fatigue. But also another type of muscle tissue is fast twitch, and these have poor aerobic capacity and is not don't have so much mitochondria, don't have so much myoglobin, but but when it works, it uses more energy for us. So it provides more energy, but it fatigues also easier. And why is the myoglobin so important part here? Because oxygen have a very high affinity to myoglobin, creating hemoglobin. So this is basically why this myoglobin is so important. Okay, yeah, and basically this anaerobic energy system, here we don't have any Krebs cycle or etc, and is active from the 10 seconds up to 1 minute, and doesn't use as much oxidative, don't have a high level of oxidative capacity because it uses anaerobic enzyme like creatine kinase, myokinase, phosphorylase, phosphofructokinase, lactate dehydrogenase. And all of these are anaerobic enzymes, so these doesn't work as good in oxygen demanding environment. Now, which are the methods for determining oxidative capacity? And these could then be explained as the O2 levels and lactate threshold. So basically, the increase in oxygen uptake is increasing with the power output. So basically, we talk here about the VO2 max. The higher the VO2 max you have, the more you are reliable for aerobic capacity and your reliance to anaerobic glycolysis. But also, you have this lactate threshold. And it's also related to the oxidative capacity. How? Because this lactate threshold here, right here, tells you that after this section, here we are using lactate as a source of energy. And highly trained people with a high level of VO2 max, these I don't know exactly, but these could have their LTL maybe right here. Here you find their LTL and not here. And this means that they would not rely as much for lactate as source of energy during exercise, more rather than using the aerobic glycolysis or using oxygen pathways. And this is so good because it tells us that this person is trained, and also because lactate leads to muscle fatigue. So if you have a high VO2 max and high lactate threshold, you also are more reliant against fatigue. Your muscle won't fatigue as easy. But also here, what is this epoch system? This epoch system is basically like post-exercise system. And so after exercising, we are not stopping the oxygen consumption here. As you see right here, the oxygen consumption is not done. It's not stopped. Rather, it's just decreasing. And why is that? We think that, okay, we train, we use oxygen, but when we're not training, we are not using oxygen as much. But why are we still seeing an O2 consumption here? This is very easy, and this is because we need this oxygen to restore the phosphocreatine system used during the exercise, but also we want to remove the lactate by conversion to the glycogen. Also, the oxidation of carbon dioxide and water molecules, but also the replenishment of oxygen stores, so the myoglobin. Also, we were trying to remove the carbon dioxide that accumulated as a byproduct of metabolism, but also the increased body temperature, but also because of also high levels of epinephrine and norepinephrine, the oxygen is trying to still be active to lower these levels. And now the hormonal regulation of fuel metabolism. So you have glucagon provide glucogenolysis and gluconeogenesis, adrenaline and noradrenaline would provide glucogenolysis, cortisol provides gluconeogenesis, growth hormone and thyroid hormone lead to lipolysis, and glucose remain in circulation, and thyroid especially leads to glycolysis, but also sensitivity of insulin increase in training, so less plasma insulin is needed to let glucose be uptaken by the cell, and this is how we affect the glucose. So glucagon, of course, glucogenolysis, gluconeogenesis, the same thing with adrenaline and noradrenaline, cortisol provide gluconeogenesis, and more. You have then also hormones that will regulate fat metabolism during exercise. So in low glycogen levels, lipolysis would increase to free the free fatty acid, so it could be used as a source of energy, and is also regulated by very low insulin level during exercise, and stimulated by epinephrine and growth and cortisol and thyroid hormones. And causes of fatigue. What is the causes of fatigue? You have depletion of the phosphocreatine system, so we can't contract as easy. Also, during sprinting, glycogen level would drop, and this also affect various metabolic pathways, so as gluconeogenesis, glucogenolysis, glycolysis is being affected here. When muscle also uses more glucose than the liver is giving out, the blood glucose level will drop, so liver respond by gluconeogenesis and glucogenolysis. And also in the extreme intense training, lactic acid accumulation would lead to hydrogen release and inhibition of important enzyme for glycogen breakdown as glycolysis. But also neuromuscular fatigue could happen due to less acetylcholine being released, and this leads to also, of course, weaker contraction, or also some enzymes are hyperactive or hypoactive. And also because due to less potassium inside the cell, and this would lead to less repolarization, so we can't stimulate the next cell to release action potential and start to contract. Adaptation to aerobic and anaerobic exercises. So basically this information here, if your muscle adapt to slow twitch, the muscle will become larger, you get more mitochondria, more myoglobin, higher oxidative enzyme activity, and more fat is using during exercise. And if you adapt to anaerobic adaptation, you will type 2 will increase in cross-sectional area and more creatine kinase active, and this will lead to more ATP production. Also, it will lead to increased lactate threshold and more power, less fatigue, and more tolerance to lactate. Thanks for listening.